Hello, and welcome to Differential Equations, Chapter 1.2, Initial Value Problems. So, we have seen that an nth-order differential equation usually has a whole family of solutions, parameterized by arbitrary constants C1 to Cn, and we're often interested in initial value problems, which consist of an nth-order differential equation, together with various constraints on the value of the function at some starting point x0, typically that will be at time t equals 0, of the form solving the differential equation, subject to that the solution at the initial time must take on a certain value, the slope at some initial time must take on another value, etc. And remember that the number of conditions necessary is the order of the differential equation. These constraints that the differential equation are subject to are called the initial conditions. So geometrically, a differential equation has a whole family of solutions. And we saw an example of this last time with the Desmos graphing of one of the families of solutions that we found was the general solution to a differential equation. So there can be many solutions, and the initial value specifies on which of those solutions our desired solution must lie. So this point would correspond to that y of x0 equals y0, i.e. the differential equation must take on value y0 at x0. Oh, and I should clarify that when I say the word not, as in y0, I am saying this kind of not. It's common in mathematical language to refer to a subscript 0 as not. So we'll introduce solving initial value problems by example. First, let's verify that this is a family of solutions to this differential equation, and then we'll solve this initial value problem. So to verify that this is a family of solutions, all we need to do is plug it in. So first, what is the derivative of this? We'll need that to plug it in for y prime. Well, the derivative of this is 1 over c minus x squared. To see this, brief derivative review, recall that d dx of 1 over x, we can think of that as d dx of x to the minus 1, same thing, and then you just pull down that minus 1 and decrease the exponent by 2, and that's the same thing as negative 1 over x squared. So d dx of 1 over c minus x, you can think of that as a composition, and we apply the chain rule. So we have derivative of the outside times derivative of the inside is 1 over c minus x squared. As the class goes on, I won't be doing this anymore, but some of you might be rusty on differentiating. So now plugging in, is it the case that y prime is y squared? Certainly yes. So this is a family of solutions. This is a solution for any constant c. Now let's solve the initial value problem. The way to solve an initial value problem is to take your general solution, your family of solutions, and find for which constant c the initial condition is satisfied. So very directly, y of 0, well, this is y, so we plug in 0 for x in our equation, and that must be equal to 2. And that gives us an equation where we then just solve for that arbitrary constant. So we find that c is 1/2. So the solution is 1 over 1/2 minus x. And that's perfectly fine, but if we want, we can simplify it. Just because fractions within fractions tend to be aesthetically not nice. So we can multiply it by 2 over 2, which is a fancy way of writing 1, so it doesn't change anything. And that looks nicer. So that is our solution to the initial value problem. And I want to emphasize that this is perfectly fine. This is the solution to the initial value problem. It can just be simplified, and simplifying is nice. I think it would be good to visually illustrate what this solution looks like. So here's our general solution, 1 over c minus x. And you can see that as c varies, we have this family of solutions. And what we have found is that when c is equal to 1/2, then y of 0 is 2. So that is the unique solution satisfying that initial condition. Every other solution does not have y of 0 equals 2. Now I also want to illustrate slope fields. So remember that our differential equation was dy dx equals y squared, and that's what these first two are saying. So that means that at every point x comma y, then the slope must be y squared. So you can see here that when y is 0, the slope is 0. Each of these little line segments shows the slope. And as y gets bigger and bigger, then, well, y squared gets bigger and bigger, so the slope gets steeper and steeper. And the same thing happens down here. For negative y squared is positive, so the slope is still always positive down here, and getting steeper and steeper as y gets more negative. So any solution to the differential equation must have the indicated slope at every point. So in other words, any solution must lie tangent to these pieces of slope on our slope field at all points on the line. And this is a nice way of seeing why there is a whole family of solutions. So any one of these you can see lies tangent to the slopes at every point. And it's just that the particular one that we wanted was this one. So that's the idea behind solving initial value problems. You take your general solution, and then you plug in the initial value and solve for that unknown constant c. And now to illustrate intervals of definition and how we've narrowed down our various possible intervals of definition to 1, let's find the relevant interval of definition here. So we can't divide by 0, so we know that that denominator can't be 0. Solving for x is not 1/2. So our possible intervals of definition are negative infinity to 1/2 and 1/2 to infinity. However, now that we have an initial value, what we want to do is choose the interval of definition that contains that initial value, since we know that this point 0, 2 must lie on our solution. So that interval of definition says 0, 2 lies on our solution. And that means that the interval of definition must be this. And that's because this tells us that x equals 0 lies on the curve, and that initial value told us that y of 0 is 2. So that's an x that must lie on the curve. And this other interval of definition does not contain that initial value. So going forward in this class, generally whenever we're asked for an interval of definition, this is how we choose the unique interval of definition, because we will be given some point that must lie on the curve. So you try your hand at this, verify that this is a family of solutions to this differential equation, and then solve this initial value problem. I encourage you to pause the video. So y prime, we'll need that. That is this, that's derivative of outside times the derivative of the inside. This minus sign just hung out there, and then we have another minus sign from the derivation. So we have this. And now we plug into our differential equation. And we get a truism. Okay, so this is a family of solutions to that differential equation. Now let's solve the initial value problem. So plugging in, y of 1, which is negative 2 over c plus 1 squared, must be equal to 1. And we have an equation where we then just solve for c. So multiplying both sides by c plus 1, we have this. and thus c is -3. So what's the solution of the initial value problem? Well, we just take that -3 and plug it back into here, and we get, and if we wanted to, we could rearrange this as this, just because it looks nicer. Okay, and what's the interval of definition? Go ahead and pause the video. So we need to find the domain of this. We can't divide by 0, so we solve for when we're not dividing by 0, and we know that x cannot be plus or minus the square root of 3. So our possible intervals of definition are these. And in which one does the number 1 reside? After all, we need our starting point x to be within it. Well, it's in that interval of definition. So our interval of definition is -√3 to √3. Now recall that one can also have implicit solutions to differential equations, and these can also have initial value problems attached to them. So let's use the fact that this is a one-parameter family of solutions to this differential equation. One parameter just means that it has one unknown constant to find an implicit solution to this initial value problem. And by the way, verifying that this is a solution is almost identical to a problem that we did in the previous lecture. Okay, so we have this initial value, that y of 2 is -6. And we know that 3x squared minus y squared equals c is a general solution. And this 2 is the x, and -6 is the y. So all we do is plug in, and we solve for c. It becomes that, and we get that c is -24. So 3x squared minus y squared is -24, also known as y squared minus 3x squared is 24. Now the next part is to sketch a graph of the explicit solution to this problem. And this is where there is a little subtlety. So the full graph of this relation looks like this. One way to see this is that if y is 0, then we have -3x squared is 24, which is impossible since that's a negative positive. X squared is always positive, so it has no solution when y is 0. So it has to be facing that way rather than this way. However, this is not the graph of an explicit solution to this initial value problem, because this part up here can never be reached from this point. So the explicit solution to the initial value problem would be the solution, which must be a function. This whole thing doesn't pass the vertical line test to begin with anyway, which lies on the curve that is accessible from the initial value. So this whole part up here is inaccessible from the initial point. The explicit solution is this one. All right, now that's initial value problems for first order differential equations, which have only one unknown constant. However, second order differential equations in general have two unknown constants. And these can also have initial value problems, but because they have two unknown constants, they need two conditions. So for a second order differential equation to get a unique solution, we'll need to be given both a starting value as well as the slope at that starting point. So that we have two conditions to nail down the two unknown constants. So we verified in the previous section that this is a family of solutions to this second order differential equation. Let's solve this differential equation subject to these initial conditions. So this operates the same in principle as the previous examples, except that now we'll have two equations stemming from each of these two conditions, and we'll need to solve that system of equations. Because in this one, we'll be plugging into y prime, let's find y prime first. Okay, that is y prime, And now we're given that y of 0, which is c1 e to the 2 times 0 plus c2 e to the 3 times 0 must be equal to 2. And we're also given that y prime of 0, which is 2c1 e to the 2 times 0 plus 3c2 e to the 3 times 0, that is equal to 3. And e to the 0 is 1. So we have from this the system of equations, c1 plus c2 is 2, and 2c1 plus 3c2 is 3. And now it's just a matter of solving this system of equations, and we have found our unknown constants. I'm sure you learned how to solve systems in the past. One way of solving a system is called the substitution method, in which you solve for one of the unknowns in one of the equations and plug that into the second equation. This always works. However, it's generally faster to use the elimination method, which looks like this. What we can do is eliminate one of the unknowns immediately by adding or subtracting the two equations from each other in such a way that one of them cancels out. So in this case, we could subtract 2 times the second equation from the first equation here. So that minus 2 distributes to all pieces. It's just multiplying the whole equation by minus 2 on both sides. And then we have 2c1 minus 2c1 goes away. We have 3c2 minus 2c2. You have 3 minus 2 is 1c2 left. And we have 3 minus 4, negative 2 times 2, is minus 1. And you can see that that just immediately gave us what c2 is. And now we can expediently get the other unknown by substituting that in. And we have found both unknowns. And now that we have found those, we have solved the initial value problem by just taking these two and plugging them back into our general solution to get our specific solution that satisfies the initial conditions. So the solution to the initial value problem is that y is 3e to the 2x minus e to the 3x. Just plugging these in for c1, c2. And one can always verify that one hasn't made a mistake by checking the initial conditions. So if we plug in 0, we have 3 minus 1 is 2. And if we plug 0 into the derivative, we have 6 minus 3 is 3. Remember, take the derivative of this first and then plug in 0, and you'll get 3. Okay, so here's a problem. First, verify that this is a family of solutions to the second order differential equation, and then solve this differential equation subject to these two initial conditions. Pause the video, take a moment. So first, to verify, we need y double prime so that we can plug it in. First, y prime is that, just taking the derivative, and y double prime, taking the derivative of that, is this. So now, plugging these in, we have that, and you can see that things just cancel out immediately, and we do have 0 equals 0. So that is indeed a general solution. And now we need to solve for c1 and c2. Okay, so y of 0 is 2, plugging in 0 into this, and setting it equal to 2, we have our first equation. And also y prime of 0 is 3, so plugging that in, we have that. Okay, and evaluating these, sine of 0 is 0, and cosine of 0 is 1. So we don't even need to do any work. We have that c2 is 2, and c1 is 3. So the solution to the initial value problem is y is 3 sine x plus 2 cosine x. Now, in all of these cases, our initial value problems did have a unique solution. But the question is that always the case, that it has a solution? And if so, is the solution unique? So let's consider a first-order differential equation subject to an initial value. Here's the existence of the unique solution theorem. Let me draw a picture to help make this more clear. So if R is a rectangular region on the xy plane that contains the point x0, y0 in its interior, and if both this f of xy and del f del y, the partial derivative, are continuous within that region, then there exists some interval around x0 and a unique solution. So if this condition is met, then we'll have a segment on which we have a unique solution around that point. Let's show an example of an initial value problem without a unique solution. Consider dy dx is x times y to the 1/2 with initial value y of 0 is 0. It can be verified that both y equals 0 and y equals 1/16 x to the 4th satisfy this initial value problem. Here's a picture of that. And to verify this, all you do is plug it in. So if y is 0, then y prime is 0 and y is 0, so that's a solution. And if y is 1/16 x to the 4th, then plugging in, we have that. Power of 1/2 just means the square root. Root of 16 is 1/4. Root of x to the 4th is x squared. So that is also a solution. So what went wrong, quote unquote? What made it so that this does not have a unique solution? What went wrong is that this part of the condition failed. So yes, our f of xy is this guy that is indeed continuous, but this guy fails to be continuous for this problem. Let's show that. Okay, del f del y. Remember that when we take the partial derivative with respect to y, that means that we're holding the other variable constant. So just imagine that x is a number like 5, it's constant. All it does is hang out there, and we're just taking the derivative of y to the 1/2. If you want to recap on partial derivatives, go back to the 1.1 lecture. So that's that partial derivative. And we can rewrite this as x over 2 times the square root of y. And look what happens. We are dividing by 0 at y equals 0, but y equals 0 happens here. And that division by 0 creates an asymptote, and that means it is not continuous there. So it's that failure of that condition that allowed this initial value problem to have two solutions. Crucially, if y of 0 were, say, 1, so hypothetically, if this were a 1 right there instead, then we would be passing through this point, and then there would be a unique solution, because this guy is continuous there since we're not dividing by 0, no asymptotes, no discontinuity at that initial value. It's just the fact that for this specific problem, where we did have a value of y equals 0, and thus a discontinuity, that made this not have a unique solution for this particular initial value. Worry not, though, these types of cases are very rare, and we'll very seldom encounter them in this class. For the most part, you can just always assume that initial value problems have a unique solution. It's not a perfectly safe assumption, but it's a good rule of thumb. All right, that does conclude the 1.2 lecture, and have a great one.